Okay, so we're continuing with chapter 6 and bending, and we're going to talk about the deformation of a straight member. We're going to think about it in terms of a rubber bar so that we can see the deformation. It's a good thought experiment. So this is the diagram we're going to keep in mind where we have a neutral surface, which means below in the positive, well, above in the positive y, when a moment's applied, compression will occur, and then in the negative y, tension will occur. And this plane here is indicating where nothing is happening, so the lengths of these fibers would stay the same. And we call this the longitudinal axis of which the moment is going around, and then y here is our axis of symmetry. So for now, we're going to limit this to beams with a cross-sectional area that's symmetrical with respect to an axis, and the bending moment is applied about an axis perpendicular to the axis of symmetry. So later in the chapter, we'll get more into other types of cross-sectional areas. Then we have 3 assumptions that we need to keep in mind regarding the way the stress deforms the material. So the first one is that the longitudinal axis x, which lies in the neutral plane, does not experience a change in length. So these are the idealistic ways we make this work. All cross sections of the beam remain plane and perpendicular to the longitudinal axis during deformation, and any deformation of the cross section within its own plane will be neglected. All right, now we can talk about how to find strain in this case. So what kind of strain this stress produces of the moment. So in the case of this member fixed to the wall, and we have these axes, the longitudinal axis, and the moment being applied upwards in this direction, we're going to take out a section so we can think about this in a differential way. We have a delta x, and then this distance down the longitudinal axis. We have our little segment here separated out. Y is the distance of any segment S that we're examining, and the distance is the distance from the longitudinal axis to that segment. And then the x is, of course, the width of the differential we're examining. So this is the undeformed state, and when we think about the deformed state in terms of that moment and the action, we can designate this distance, O, from the center of the curvature to the longitudinal axis, which is now curved, and rho is the radius of the curvature of the longitudinal axis. And we now have this delta theta to describe the angle of deformation, and the new delta S. So the segment here, S, is what's changing, and we assume that delta X stays the same. So now we can say delta X is equal to the original segment length, delta S, which is also equal to rho times the change in the angle. And we know that the change in the segment length is equal to rho minus y times the change in the angle. So we can use that, we use our definition of strain, and we can say for 2 cases, the limit as the change in the segment length goes to 0 is the new change in segment length minus the original over the original. And these are just based on our original definitions of strain. And then the limit as the change in the angle goes to 0 is rho minus y times delta theta minus rho times delta theta over rho delta theta. Therefore, using this proportionality will be really handy for us. We can say that the strain is equal to negative y, this distance to the segment, over rho, this radius of curvature of the longitudinal axis. Okay, so that tells us something that's really important, just theoretically, that the longitudinal normal strain varies linearly with y from the neutral axis. So linear relationships are always great. Since the maximum strain is equal to C over rho, so C is just the distance where maximum stress occurs, the longest distance away from the longitudinal axis. We can use our strain relationship that we just found along with the maximum strain to determine that the strain equals negative y over c times the maximum strain. And this is just a note writing out what I was saying earlier, how can always keep in mind that when there's a contraction, which always occurs in the positive y, that's negative strain, and an elongation, which occurs in the negative y, is a positive strain. So that's our standard there. And this is just a little diagram more explaining some of the variables I'm using. So this is how we describe the strain on a member and bending. And now we're going to use that information to develop the flexure formula, which you guys will use in solving problems for this chapter a lot. So we're going to develop an equation that relates the stress distribution in a beam to the internal resultant bending moment acting on the beam's cross-section. So assume the material behaves in a linear elastic manner. A linear variation of normal strain must be the result of a linear variation in normal stress. Because of the proportionality of triangles, or we can use Hooke's law, sigma equals strain times Young's modulus, stress equals strain times Young's modulus. We know that the stress here is equal to negative y over c times the maximum stress. So we can locate the position of the neutral axis on the cross-section by satisfying the condition that the resultant force produced by the stress distribution over the cross-sectional area must be equal to 0. So this is what we've done lots of times before. We're just talking about using resultant forces and resultant moments. But we're just keeping in mind that it's over the cross-sectional area. And so the resultant force produced by the entire stress distribution has to be equal to 0. So we go back to that, like our original assumption. We can say the resultant force is equal to the sum of forces in x, because that's all we're concerned with in this case. And so we set that up. 0 is equal to the integration over the cross-sectional area of the force, which is equal to, as we know, sigma change in area, which is equal to this formula that we've just derived up here, negative y over c times the maximum stress times the change in area. And we can pull out the maximum stress over c, and then we have this isolated here. This is what we're going to integrate, and we have essentially that integration over the area of y dA has to be equal to 0. So that tells us the first moment of a member's cross-sectional area about the neutral axis must be 0. And that can only be satisfied if the neutral axis is also the horizontal centroidal axis for the cross-section. So we know where the neutral axis needs to be. And we can determine the stress in the beam from the requirement that the resultant internal moment must be equal to the moment produced by the stress distribution around the neutral axis. So in this case, we're making this equivalency where the resultant moment that you find with respect to z is equal to the sum of the moments around z. And then we can integrate over the area with respect to y and the change in force. And we can plug in there for the relationships we already know. And working out, we get down to where we have the moment of inertia of the cross-sectional area about the neutral axis. So the moment is equal to the maximum stress over c times the polar moment of inertia. And we can rewrite that to be something more useful for us in our situations based on what we're given. And the flexure, one variation of the flexure formula would be that the maximum stress is equal to the moment times the c distance, which I have here, the perpendicular distance from the neutral axis to where the maximum stress acts, over the polar moment of inertia for that geometry. And because we know already that the maximum stress over that distance has this relationship, negative stress over y distance, we can also say that stress in general is equal to negative moment times y over polar moment of inertia. And both of these we refer to as the flexure formula, just depending on what you need in your problem. You can use either. And a few definitions about variables I'm using. Sigma max here is the maximum stress, which of course is acting at a point on the cross section furthest from the neutral axis. And m is the resultant internal moment around the neutral axis. And then c, perpendicular distance from the axis to the farthest distance, so where sigma max acts. And then next time we will finish up chapter 6, and you should have everything you need to finish your homework. I have one example. So problem 650 in the book, they want us to determine the largest moment without exceeding the maximum allowable stress and tension or compression. And we're given that the maximum allowable stress and tension is 22 KSI, kips per square inch, and then maximum allowable stress and compression is 15 KSI. So the distance to the centroid from the base, we can find these kind of equations in the back of the book for any geometry, and we know it's an equilateral triangle. So we plug in information from the diagram, and we find that from the bottom to this point, which is our neutral axis, it's 1.15 inches. And then we can go ahead and find the polar moment of inertia, which we find is 4.6 inches to the fourth. And now we're going to think about what is the failure situation due to tensile stress. So the maximum stress from the equation, the flexure equation we just found, the moment times y over I, is given to us. 22 equals the moment we're trying to find times y, which we've already found, and also the polar moment of inertia. We plug that in, and we have 7.33 kip feet. Now failure due to compressive stress, we use the other case, the other formula we found, and we say 15 is equal to this moment times this distance c over the polar moment of inertia, which we already found. And we get that the moment here is 2.5 kip feet. So this being a smaller moment means it's the limiting moment, so it's going to fail quicker in this mechanism, and so that's what we need to be concerned with. So that's one example of how we use these, and there are more in your homework problems that will be slightly different, but of course, let me know, email me if you have questions.